So I'm just going to give a generalized overview of aerobic respiration first, and then we'll go into the details. And I think it's useful to do it this way, and then we'll pan out again. So we're going to have a panned out generalized view, a very close-up view, and then a panned out view again. And the reason for this is I think that the reason I never get students who remember the electron transport chain, even if when they took their prereqs a term ago. And I think the reason is students miss the forest for the trees. You know, it's such a complicated biological process, and you're required to memorize all these minute features, and that makes it hard to remember the main purpose. It makes it hard to, so that all students end up doing is memorizing without any concept of what's really going on, without the broad picture. And that makes it difficult to remember, mostly because there's no story behind it. It's just, you know, tiny little minute details lost in empty space in a way. So the whole point of aerobic respiration is to harvest energy from sugar and other high energy molecules. That's the point. So when you get to the electron transport chain, please remember that. It's part of the process of harvesting energy from food, okay? So the whole point of aerobic respiration and the electron transport chain is to harvest energy from food. You know that there's calories in food. You know that those give you energy to run on the treadmill or whatever it is. You know, take care of your kids or whatever, right? So this is we're looking at that process now. You know that you're feeling low blood sugar, low energy. You eat some food, you feel better. Why? This is why, right? So the way that our cells harvest energy from food is by stripping food from its high energy electrons. So food, high energy foods are things like sugar and fats, okay? The reason they're high in energy, sugar is a molecule, glucose, fructose, lactose, those are all different kinds of sugars. They're high energy molecules. Why? Because of unstable electron configurations. There is potential energy packed into these molecules because of their high energy electrons, low stability electrons, right? So you strip those high energy electrons from food and put them into more and more stable configurations. Energy is going to be released from them because remember, energy is never created or destroyed. It's just moved around and converted from one form of energy to another. It never disappears, right? Energy in the universe is constant. So you have to extract the energy from your food and convert it into a usable form for the cell, which is ATP. Okay? So our cells do harvest energy from food by stripping food molecules like sugar of its high energy electrons. The energy from these electrons are used to generate ATP, the energy currency of the cell. That's the form of energy every single piece of the cell can recognize. Any energy requiring reaction in the cell can recognize ATP and use ATP. That's how the cell's set up. All the energy that comes in the forms of different kinds of high energy food molecules have to be converted to ATP, just like all different kinds of currencies of the world. When travelers come to the United States, all their money gets converted, all the currencies get converted to the US dollar. US dollar can be used anywhere. You can't go to a random store and pay in rupees, right? You can't go, so sugar molecules can't come in and just go pay for energy requiring reactions, right? They have to be converted to the same consistent molecule for use all over the cell, and that's ATP. So our cells strip sugar of its high energy electrons, and the energy from those electrons is used to generate ATP. So let's look at this. So the whole point is to harvest energy from sugar by stripping sugar of electrons, high energy electrons, and then use the energy that was once in those electrons to generate ATP, the energy currency of the cell. So by now, this equation at the bottom of the slide should be familiar. We eat sugar and breathe oxygen, and we produce some waste products like carbon dioxide and also energy in the form of ATP. So carbon dioxide and water are waste products of aerobic respiration. So we don't need these. I mean, water's great, right? There's no problem with water. We need to get rid of the carbon dioxide, but water is no problem, but it is a waste product. It's not the purpose of aerobic respiration. We're not doing this to hydrate. We're doing this to get the energy. And that energy then gets packed into ATP, which can be used anywhere in the cell for any energy requiring reaction. Now, this is the exact same equation as what happens when you burn a log in your fireplace, and it's actually the exact same equation as when you burn fuel. Yes, lignin, which is wood, that's a very similar molecule to glucose. It's a carbohydrate, right? But of course, this process goes forward with fats with only minor modification, right? Because we also harvest energy from fats and stuff. But the equation would be slightly different, but it's mostly the same. Okay? And so the same thing happens with, so fats are hydrocarbons, fuel for your car is a hydrocarbon. It's the same thing. You put these, whatever this is, just glucose, lignin, butane, fats, this could be replaced with any organic molecule. Plus oxygen, carbon dioxide is emitted, water is emitted, and energy is released. But when you do this in your fireplace, the energy that's released is not harnessed for anything useful, right? If you're burning a log at a campfire or in your fireplace, it gets released as heat and light. So it's useful in that it can warm you up and it can give light to your area, but it's not harnessed in as efficiently as the energy harvested in your cell. And that's because it's all released at once. The energy extraction process in your car is a little bit better. You get a little spark and it lights a small amount of fuel, which explodes basically and creates this this pressure outwards, which drives certain components of your engine so that the car can move forward. And so because in your engine only small bits of fuel are being released and the energy released from them at a time, the car can more efficiently use that energy to move forward, right? Because it's not, if you exploded the whole gas tank at once, you'd lose most of that energy in flame and in heat and in light. And you wouldn't be able to harness all that much energy to move forward in your car. So your car is even less efficient than your cells. And the reason is the energy is released in small steps. So that's more similar to your engine, right? You don't release it all at once. You release it in these small steps so that more and more of this energy can be used usefully, harnessed in a useful way. Some of it does get lost as heat, right? That's why when we're burning through our sugars, when we're burning through our fats by exercising, we get hot. We sweat, we get hot, so our body temperature rises because we are literally burning that sugar just like you'd burn a log. So some of that energy does get lost as heat, but by doing it this way, you can maximize the amount of energy that gets harnessed in a useful form, the useful form of ATP. So there are three main steps of respiration, and those are glycolysis, the Krebs cycle, and the electron transport chain. And so, in this slide, you see the energy is released in tiny steps. Well, here's three of those steps, but each of these steps can be subdivided into many, many, many other steps. And when I was in AP Bio in high school, I had to memorize every single step of glycolysis, every single step of Krebs cycle. I'm not going to make you do that, right? Because I want you to understand the main points. I will show you diagrams of every single step. You do not need to memorize every single step. You need to memorize the overarching themes. So this slide I would like you to memorize. So glycolysis is the first step of aerobic respiration, and it's subdivided into several steps that we'll see on the next slide. But the main thing is you get 2 ATP out of this, 2 of those energy currency molecules that can be used in the cell. And you get 2 NADH. So remember we loaded up 2 of the electron carriers with high energy electrons. So 2 NAD plus became 2 NADH. So 2 NAD plus were loaded up with high energy electrons, making them into NADH. So this is not useful for the cell yet, but it's carrying high energy electrons, which will be used to make more ATP later, because 2 ATP from glycolysis, that's not very much. Okay. And then the next step is pyruvate oxidation plus the Krebs cycle. I like to lump these together. Some textbooks will separate them, but I lump them together because pretty much the same thing is happening here. It's to the same end. Okay. And I'm going to go back through each of these steps and give you more info on each step. So pyruvate oxidation and the Krebs cycle, when you take them collectively, 2 ATP are generated, and 8 NAD pluses are loaded up with high energy electrons, becoming NADH, and those, again, there's just high energy electrons are being stored to make more ATP later. And 2 FAD molecules are loaded up with high energy electrons, becoming 2 FADH2. So I want to emphasize that it's sugar and other food molecules going in, okay? So, fats come in different places than sugars. Sugar is the only thing that goes through cleanly. That's why we follow glucose. But other high energy molecules like fats go through as well, but they come in at different spots. They have more modifications, so we don't talk about them, but it's basically the same idea. And so what's happening here is, how are these 2 ATP made? Well, ATP is this high energy molecule. The energy comes from the food that you ate. So the energy here is, remember, energy is not created or destroyed. It's not that the ATP generated energy out of nowhere. It was just moved from the food to the ATP. The energy was in the food. Now it's moved to ATP, okay? This was a low energy molecule, ADP, and the energy in the food drove the synthesis of a higher energy molecule, ATP. So energy was transferred from the food to ATP here, from the food to ATP here. High energy electrons were placed in NADH and FADH2. Those are going to be used to make more ATP later. But all of this energy for ATP production is coming from your food. The third step in the electron transport chain, the third step in aerobic respiration is the electron transport chain. And some textbooks will divide this. I'll just usually say electron transport chain, and that'll cover the electron transport chain and chemiosmotic phosphorylation. But some textbooks will divide these up. But they all are. To me, again, they're all to the same end. This step, the electron transport chain, and chemiosmotic phosphorylation, they go together. They're part of the same step. So I'll usually just refer to them collectively as the electron transport chain. And in this step, all of these electron carriers that are carrying these high energy electrons, they pass their high energy electrons to this step, to the enzymes in the step, and those enzymes use the energy from those high energy electrons to generate a huge amount of ATP. It's 28 to 32 ATP per glucose, and that's another thing I should mention here. This is per glucose molecule, so 2 ATP per glucose in glycolysis, 2 ATP per glucose in the Krebs cycle, and 28 to 34 ATP per glucose in the electron transport chain. Now the energy from this ATP ultimately came from sugar, but there were these middle steps, right? Because in glycolysis and in the Krebs cycle, high energy electrons were being stripped from food, and then they were brought here to the electron transport chain to make more ATP. Okay, so the energy in those electrons that came from your food drives ATP synthesis here. All the NADH it's given off its electrons, so now it reverts back to its electron poor form, NAD+. All the FADH2, it's given off its electrons, its high energy electrons, so it's reverted back to FAD, its electron poor form, right? The main point here is generating this much ATP. So this is the main energy harvesting step right here, but it can't happen without these first 2 steps. So in this slide, I show you how much ATP is generated in each step, and I show you where the electron carriers are loaded up and emptied, right, in each step. But there are other main points for each step. So glycolysis, you can see the main point is in ATP production, because not very much ATP is generated, relatively speaking. The main point, and also not very many electron carriers are loaded up with high energy electrons. The main point of glycolysis is to destabilize sugar enough that it can react and start falling down its energy hill. It can start being broken apart and releasing its energy. And this harkens back to the concept of activation energy, which we covered in a previous lecture when we talked about enzymes. So glucose, fats, those are high energy molecules, which means they are unstable. But remember, I stated that they are in sort of like the stable energy nook, and they need to be perturbed a little bit before they can react. That's why they are not spontaneously, and that's why sugar is not spontaneously combusting in your sugar jar with oxygen. It needs to be perturbed a little bit and destabilized a little bit before it can start reacting and releasing all of its energy. It needs to get over that activation energy hump. So that's the main point of glycolysis. So we'll go into glycolysis in more detail in the next slide, but what you actually do here is you invest 2 ATP, then get 4 ATP out. You invest 2 ATP because you're investing energy, which is destabilizing glucose, and then 4 ATP come out for a net gain of 2 ATP. Okay? So glycolysis is about destabilizing the sugar. Krebs cycle, which by the way, some textbooks say citric acid cycle, is the same thing. I'm sorry that there are two names. I don't have any control over that. But different things that you read on the internet, different textbooks that you might have, will sometimes say citric acid cycle and sometimes say Krebs cycle. Krebs for the doctor that discovered it. Citric acid cycle is named for the molecules that start it. Okay, so in this step with the Krebs cycle or the citric acid cycle, you can see here again, not much ATP is generated. That's not the main point of this step. But what you do see is that a huge number of high energy electrons are stripped from sugar. There's 8 NADH per glucose that are loaded up with high energy electrons. And also this other electron carrying molecules loaded up as well, FADH2. This step is about stripping food, your food stuff, from its high energy electrons. You are just stripping off those high energy electrons here. And that's an investment measure, right? Because these high energy electrons, they're not used to generate ATP in this step, but they are used to generate ATP in the third step of aerobic respiration. So glycolysis is about destabilizing sugar to get it to react. Pyruvate oxidation in the Krebs cycle is about stripping those high energy electrons off of the sugar so that they can be used later for ATP production. And then the electron transport chain, obviously the main point here is to generate ATP. So what happens here is all of these high energy electrons that were harvested in these first two steps, but especially in the Krebs cycle, are used to make ATP. Okay, so this is the main point of the electron transport chain, is ATP production. So again, glycolysis, destabilize sugar. Pyruvate oxidation in Krebs cycle, strip of electrons, strip the food of electrons, which by the way is oxidation, right? When you take electrons from something, you're oxidizing it. Loss of electrons is oxidation. Leo the lion goes grr. So you're completely oxidizing those food molecules, completely stripping them of electrons. Electron transport chain and chemiosmotic phosphorylation, using the energy in those high energy electrons that you strip from food to generate all that ATP, which is the energy currency of the cell.